Okay. If there are none, then we'll go ahead with this. Uh, this is basic course on computer systems and programming to make you familiar with this powerful tool and the immense potential that it holds to help you increase your productivity. So, to start and to set the tone, let me share this brief presentation by Professor Nick Higam. He is a professor of mathematics at the University of Manchester, and he brings out the basic idea that I wanted to uh, share with you: the power and the limitation of digital computer, the uh, most ubiquitous tool that you will find these days in any engineering and science program, including architecture, right? So, can you count on your computer? So, it's a pun on the word count, and the emphasis is on both interpretations of the word count. Can you literally count 1, 2, 3, 4, or can you rely on your computer? That's another interpretation of this word count. So basically, scientific computation is something very complicated formula that you derive at, but then how do you analytically compute this? I mean, this is not for feasible for a normal person to make sense of this kind of equations. And for that purpose, computers are very handy, which can help you to reveal the information that lies concealed in these kind of expressions or equations, right? So the idea is the person who knows this would probably think that a general person, general public would be able to understand it. But it is the computers, the basic number crunching that will sample this data and generate the graphs and plots, beautiful visualization that is possible using computers. So that is what is more appreciable, and you can understand, you can interpret the results in greater detail if there is some graphical mode of presentation and some way or different dimensions can be explored uh, in a more easy to understand way. So that is what the computers are essentially used for, to make any subject approachable to common public. Now, in order to make it approachable, and in order to make it understand, or in order to talk and in a particular way which can be understood by the computer and humans as well, so there is of course some kind of encoding of information that happens, and that's how the entire information theory has progressed. So just to tell you, if I ask computer to count up to 6, right? So that's what Professor Nigam proposes, that he's using a computer and he performs simple tasks, 6 tasks. The result of those 6 tasks should be these numbers: 1, 2, 3, 4, 5, and 6. But when it was computed, when these simple six numbers, first six numbers, decimal numbers, a computer was asked to compute, the result that we get is 1.000000000, 2.00000, and then something at very far away place 1 1, and then 3 is not computed at all. Instead, you what you have is 2.99999, so on. And then when you try to compute 4, you just get 1, completely off the mark. Then you try to compute 5, you get a result which is seems very weird. Anybody recognizes this field or this symbol NaN? What does it mean? Can anybody tell what is NaN?
Not a number, sir. Not a number.
Yeah. So it is essentially an operation, mathematical operation, which is not defined, right? So the result, I mean, it would be something like trying to compute logarithm of a negative number and so on. So that is what it results in, not a number. And then finally, it is inf. Instead of computing 6, the computer reports INF. So that stands for infinity. That's a shorthand for infinity. So we'll see how this simple number crunching fails so dramatically, and therein lies the uh, lesson about being vigilant while using computers. So, is this a flop? Again, pun on the word flop. This result is, of course, completely flop. But what he's referring to here is floating point operations. That's the unit in which we measure the speed of computers, right? So flop is floating point op, and if we just add s next to it, capital S, not this lowercase s, then that is floating point operations per second. So initially, the first computers, I mean, first during Second World War, the computers were uh, extensively used for cryptography purposes, and they could actually the machine that they used was one floating point operation, and it took 300 seconds to perform one floating point operation. So essentially 0.003 flops per second. So 1950s. So this was in Second World War around 1945. 1950s technology developed, and from 003 flops you could achieve one flop per second. Then Pentium 4, we could achieve 4,000 million flops per second. Then supercomputer NEC, Earth Simulator, it could achieve 35 million. So million is 10 raised to the power 12. So that is what it could achieve. And now we have in our campus uh, that is petaflop machine. So 10 raised to the power 15, I guess. That's the compute power that we have in our supercomputer that we commissioned recently in our computer center. So you may like to have a look at that Param Ganga. So that is the uh, supercomputer that we have installed in our computer center recently. So these are the old pictures of earlier computers. So Pilot S, and then this is the Earth simulator, the cluster of units which are interconnected through high speed network. So even our Paramganga layout is something similar. These are individual units which are interconnected through high speed network switches. So this is another example of Earth simulator. So floating point number. So floating point number, do you have any idea about what is meant by floating point number? Why is it called floating point number? Anyone?
Sir, I heard about floats as decimal numbers, I think.
Well, decimal is a base 10 number system. Floating point can be anywhere. I mean, okay, let's talk in terms of base 10 number system, because we are humans evolved uh, by counting on fingers, and since we have 10 fingers, so that's how the base 10 number system comes naturally to us. We feel more comfortable counting in multiples of 10. So that's how decimal number system comes very naturally to us. But that is not to prevent any other or take away from any other number system base of the number system. But that decimal point that you have, I mean, let's take 3.14 pi. So what is that decimal point? What does it indicate?
So that a fraction number after the
Yes,
whole number.
that is essentially a separator between the whole part and the fractional part. And the way we write, I mean, the number system that we write, so 3.14 is essentially equal to 3, that is the weight, multiplied by what is the uh, position value. So that is 10 raised to the power 0, right? So I would just say, let me share this whiteboard. Yeah. So 3.14 is, are you able to see the whiteboard?
Yes, sir.
Okay. So 10 raised to the power 0 plus 1 multiplied by 10 raised to the power minus 1 plus 4 multiplied by to the power minus. So this is how numbers are encoded. So this 10, that indicates the base of the number system. So if we are using decimal number system, so we are encoding numbers in as multiples of different powers of 10. So this decimal point separates the positive powers from the negative powers of 10, right? And this can be actually floated around. So this number, I can as well write this as 0.314 multiplied by 10 raised to the power 1. I can write this as 0.0314 multiplied by 10 raised to the power 2. Right? So the whole point, the whole idea is this separator can be shifted whichever way, right? I can also write this as 1.4.
Excuse me, sir.
Yes,
Sir, we can't see anything on the whiteboard.
you can't see anything on the whiteboard.
Yes, sir.
Are you able to see this board?
Yes, sir, it is visible.
Okay, so apparently there were two whiteboards that I had created. So should be, so everybody is able to see this? Anybody who is unable to see the numbers on the whiteboard? Okay, fine. Yeah, anyone?
Go to the link and then you are able to see.
So, so the point is this decimal point can be shifted either to the left or to the right by suitable change of the powers of the base of number system, suitable exponent field change as multiple of the base of the number system, right? So that is what the floating point number is. And why do we need these floating point numbers? Because that allows us to encode very large numbers and very small numbers by suitable change of the exponent field. If I raise 10 to a very large number, then even if my precision is not uh, sufficiently large, but the magnitude wise, I am still able to deal with a very, very large number. And similarly, if I raise this to a very large negative power, negative exponent, right? So, for example, 10 raised to the power minus 32. So that would represent that allows me to represent a very, very small number. And it's not that these numbers are figment of imagination. 10 raised to the power minus 32, I am talking of the uh, number similar to mass of electron, right? And 10 raised to the power 10, I'm talking of speed of light, and higher even we can have gravitational constant and Planck's constant and so on. So all those numbers, I mean, when we do scientific computing, we deal with numbers which range in magnitude by a very, very large uh, margin. And we need to find a way to accommodate, to be able to represent such numbers which are very large in size as well as very
Sir,
small in size. Yes,
sir, some of us are not able to see the whiteboard, sir.
okay.
Yes, sir.
Some of you are not able to see the whiteboards. Let me see. This is fine. Well, it shows it is shared with 18 people. Let me just see. Let me close all whiteboards and open it again. This is also shared with 18 people.
Sir, like we can see the board, but it's completely white.
Yeah. So apparently you are, I mean, just close that. Close all boards that you have.
Okay, sir.
And then I shared it again, so just check the recent notification.
Sir, in the chat.
No, you should be receiving it in mail.
Okay, sir.
Any better? Okay, so five people have should be able to view now. Five people have joined. Okay, anyway, you can, I mean, you must receive this link in your ITR ID and you can access it from there. Oops. Why am I getting this request for access? I mean, I already sent the request. Okay, fine, anyway. So, coming back to our discussion, uh, so floating point numbers, they are essentially like uh, signed numbers. They are essentially real numbers, so you need to be clear about there are two different ways in which numbers are represented on a computer. There are integers, essentially two broad ways. There can be variation in integer types as well, and the other type is real. Now there can be several different formats for real numbers as well. So I I'm sure you understand the difference between integers and the real numbers. So real numbers are the ones which have fractional part. Integers are just the whole numbers, and they would range from minus negative. The range of integers or the number system, what we understand from basic mathematics, number line is infinite. It extends from minus infinity to plus infinity, right? That's what you have learned all along, isn't it? Number line, what is the range of number line?
Minus infinity to infinity. So
Minus infinity to plus infinity. Now this brings us to the first problem with computer. Computer is a man-made device. It is finite. It is finite in size. It is finite in speed. Infinity is impossible on a computer, right? So the infinite number line does not exist on computer. Computer can, no matter how big or how expensive your computer is, it has finite limitation on the size of the number that it can represent or it can deal with. And it works, that affects both real numbers as well as the integers. So when we are more on this a little later, uh, but keep this in mind, the concept of infinite number line as we understand and take it for granted is not guaranteed on computers. So floating point numbers, these are the encoding for representing real numbers, and they are represented as plus or minus, that is the sign, and then there are mantissa, and then multiplied by whatever is the base of the number system raised to the power exponent, right? And different powers of base of the number system, they represent the uh, basic idea, the numbers, magnitude of the number. So in this representation, individual these mantissa digits, they range from 0 to 1 less than the base of the number system. So you can have these digits ranging from, in the case of binary number system, they can range from 0 and 1, and in case of a decimal number system, they can range from 0 to 9. And the first number is not 0, right? D1, that's the constraint. D1 is not equal to 0. So that is the standard form. So beta is the base of the number system. It can be, in case of binary, it will be 2. In case of hexadecimal, it will be 16. In case of octal, it will be 8. And in case of decimal, it will be 10. And then number of digits that you can retain, distinct digits, that is called the precision. And this power of the base of the number system, that is the exponent range. And there is a range, as I said, computer is a finite machine, so there is a certain minimum and maximum, that the exponent can have some minimum value and it can have some maximum value. And the reason of, because of this way of representation, you will find that you can very well see that these numbers are not equally spaced, they would be distributed exponentially, right? So just for an example, just to show you visual impact of how the numbers are distributed on a computer. So just let's say, let's take a toy system where beta is equal to 2, so binary number, and 3-bit precision. So we just retain 3 digits here, and then the maximum value is the exponent is 3, and we just take the non-negative floating point numbers that we can represent using these using this number is this, right? We just take this D1, D2, D3, D1 cannot be equal to 0, so it would be 1, 0, 0, then 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are the possible configurations, and then beta raised to the power uh, 0, beta raised to the power minus 3, beta raised to the power minus 2, beta raised to the power minus 1, beta raised to the power 0, then beta raised to the power 1, beta raised to the power 2, and beta raised to the power 3. So these are the numbers that you have, and you can see that these numbers, they are all, the spacing between the numbers keeps on increasing as the magnitude of the number increases. As the number becomes large, the spacing between two adjacent digits that can be represented exactly on computer increases. What is the implication? Let's say during any computation, if your result happens to be somewhere in between, let's say 4.5, and you are using this kind of number representation, then the representation on a computer, the computer will either treat it as 4 or it will treat it as 5. It will never handle it as a 4.5, right? And this is what we call as round of error in computer arithmetic. And this round of error will keep on increasing as the magnitude of the number increases. So that is one thing that you should appreciate from this distribution of numbers. So spacing, I mean, these are these tick marks. These are the numbers that are exactly represented on the computer, on this toy computer. So these are what we call as machine representable numbers. Anything other than that does not exist on a computer. So although your basic mathematics training tells you that between any two real numbers, let's say 1.1 and 1.11, there are infinite numbers that you can pack in between 1.10 and 1.11. But that is not true in the case of digital computer. The number of numbers that can be represented are fixed, and they are distributed in exponential fashion, right? They are not uniformly distributed, and the distance between the two adjacent numbers increases as the magnitude of the number increases. Another thing that you should appreciate here is relative difference between this 0 and what is the smallest number here. Please note that the representation involved d1 is not equal to 0. So if d1 is not equal to 0, so irrespective of the fact whether rest of the digits are 0, and whatever the exponent be, exponent may be some very small value, e min maybe minus 2000 or minus 100 or so, it will still be some small number. It will never be equal to 0, isn't it? So 1 multiplied by a very small number is still some number. It is not 0. So the point that I am trying to drive at is absolute 0 does not exist on a computer. It is impossible to arrive at this result of 0 through a computation. Computation involving floating point numbers or real numbers on a computer. Integer arithmetic, yes, you can arrive at 0 as a proper result, but not impossible to arrive at compute 0 as a result of numerical computation while working with floating point numbers. So that is something that you should keep in mind. So how do we use computers, and what are the possible sources of errors, computer errors, so-called computer errors? So two kinds of errors. One is, of course, the bugs in programs. Those are unintentional. These are obviously errors. So one engineering disaster, that is the American NASA's Venus probe, was lost due to a program fault. I mean, this is a do loop I was talking. So this is certain set of instructions were supposed to repeat 3 times. So for different values of indices, I taking value from 1 to 3. But while typing, instead of comma, the operator, the programmer typed dot, and that is just the adjacent key on the keyboard if you look carefully. So instead of 1 comma 3, the operator typed 1.3, and then this loop executed only once, right? So I is equal to 1, next integer I is taken to be integer, so it does not go to up to 2, so it never did the 3 sets of calculation that it was supposed to do. So while the intention was I comma 3, the programmer typed I dot 3, and it was not detected by the compiler. It will not be detected by compiler, Fortran compiler. This is a Fortran statement, and the bug will only surface if something goes wrong uh, unexpectedly. The results do not make sense, and then unfortunately that happened during the actual project mission. It never happened during the trials. Secondly, second type of error is the limitation of the computer. As I said, numbers are finite and not all numbers are available. So it's a natural thing that average of two numbers would lie between those two numbers. So if we are working with 3 decimal digits, precision of 3 decimal digits, and if we try to take the average of 5.01 and 5.02, result is, I mean, you add them up, so 5.10.03, and you divide it by 2, and then obviously the result has to be stored in 3 digits space, so that trailing numbers beyond this point would be uh, discarded, right? So this 3 is promptly discarded. The number that is stored is 10.0, and then you divide it by 2, the result is 5. Now you have this very, very, uh, I would say, absurd result, which is arising out of a valid computer arithmetic. Average of two numbers lies outside the range, right? So this is uh, because of the vagaries of the design of point number system, that it happens and nothing can be done about it. This is how the computer is designed, and that is why it is important that you are aware of these design aspects of the computer, so that you do not uh, inadvertently uh, land up in such absurd results and then take it for granted that this has been computed by so expensive and so top of the line computer, so it has to be correct. No, it doesn't have to be correct. Then second error is again round of error. So stock exchange, how the stock exchange value increased, and then although the stock exchange was doing very well, doing good business, but uh, its result is not working out. It's not reflecting. So January 1982, the index established at some benchmark number of 1000, and in November 1983 the index was 520, right? So apparently climbing down, I mean half, So index value, stock exchange index is actually half of its original number in uh, less than 2 years, right? But the economy was doing very well. The exchange was running in profit, so there was no reason for this depreciation of the value. The problem was the index. I mean, it was the encoding. The index rounded down to 3 digits at each recomputation. So 6.678.35 was rounded off to 63678, and this is always in error. So these small fractions which were discarded, the errors were always in the same direction. And just imagine if there are millions of transactions of this kind happening every day, and you accumulate these over a period of 2 years. So these small errors actually add up to a very, very large error. And that is what the problem was, right? So again, it was a problem, and upon the recalculation of the result after correcting this error, the index actually shot up by 100%. So in 2 years, it moved from 1000 to 2000. Third one, failure, engineering failure because of poor computer arithmetic, bad computer understanding of the arithmetic on computer. So that was in 1996. The Ariane 5 rocket launcher failed only about 40 seconds after the initiation of the flight sequence, right? So it just exploded within the atmosphere about 3 kilometers above the Earth. So internal software exemption was detected because the data conversion from 64-bit floating point to 16-bit signed integer value. So integer arithmetic is faster, integer storage is faster to access, floating point arithmetic is always uh, tedious, and probably that was a decision that they will compute using integer arithmetic, and somehow the floating point number which was converted had a value greater than what could be represented by a 16-bit signed integer. So that's a finite width. Only a number of a certain size can be represented, can be accommodated. Any number beyond that would just roll back into the range. It's like a milestone, a milometer reading on your automobile, right? So after certain range, 9999999, next number, you all get zeros. Again, it starts counting from zero. So something similar. That's how the integers are represented. So this resulted in an operand error, and that entire computer onboard computer got confused and didn't know what to do and had a problem with cooling, and the entire thing just blew off. Right. So limitations of computer, as I said, the, because of the finiteness of the storage, so we are losing precision in whatever we do. Every single operation is a source of error. So we are doing inexact arithmetic, and every flop, every floating point operation may produce a small error. And because of this, some rules of the arithmetic that we take for granted, that is the associative law, does not hold. I mean, A multiplied by B plus C need not be equal to A multiplied by B plus A multiplied by C. Depends on how you perform. And similarly, commutative law need not hold. It depends on which order. I mean, A multiplied by B would incur different amount of round of error, and then multiplied by C would have different round of error than B multiplied by C and then A multiplied to this product. So these two will have a different round of errors, and they need not be equal. And similarly, square root of x would incur some round of error, and then squaring it off will not be equal to x. I'm sure this is something that you all have experienced. Uh, Take any number, very large number on your calculator, 99999, and keep on taking square root repeatedly. Eventually, you will end up with 1. And after that, no matter how many times you try to do the square of it, you just you are just stuck at 1. The original number can never be uh, recovered. So solving a quadratic equation, again, this is a very uh, classic example of error in computation because of finite precision, and you can go through this example, and that is why it is always better. I mean, this is what we call as catastrophic cancellation problem, where numbers of two similar magnitude, if they are subtracted, then they result in uh, very severe cancellation of significant digits, and the result is actually very much prone to error if you have only a small number of precision in operation computation. And therefore it is always better to rearrange the computations such that catastrophic cancellation is avoided, and then take the root, second root, by using the polynomial property that product of the roots is equal to ratio of constant term divided by the coefficient of quadratic term, and that gives us the accurate value of the second root. Again, the calculation of sample variance, difference of two numbers, that will again lead to uh, numerical errors. And this, unfortunately, these numbers, these rearrangement, they actually appear to be good when working with the notion of infinite precision of real arithmetic, but in actual computation, they are actually problems. So if you take these two examples, I mean, two alternate ways of calculating variance using these three numbers, 10,000, 10,001, 10,002, using 8-digit arithmetic, this number, this formula gives you variance of 1. The second one gives you variance of 0, right? So again, it's a matter of recognition of what are the problems, how of the encoding. And this problem is not hypothetical. These formulas, they are actually encoded in commercial offerings. So Casio calculator actually calculates variance according to this formula because it is easier, it is faster to execute. So here Casio has taken the route of using a faster algorithm and sacrificing the accuracy. So sometimes be careful when you are working with these numbers. Don't uh, believe the results that you compute blindly. And then we have very interesting example, Patriot missile software problem. So Patriot missile is a shield system which traps, which monitors the incoming missiles and then launches a counter missile the moment it detects any incoming missile to destroy it in air before it hits the target, right? So during first Gulf War in 1991, a Patriot missile defense system was operating in Saudi Arabia during Operation Desert Storm, and it failed to track and intercept an incoming Scud missile from Iraq. So this Scud missile eventually hit army barracks and it killed 28 American soldiers. And the reason was the missile's computer was 1970s design and it used 24-bit arithmetic. Again, it is a problem of finite size. So the Patriot system It tracks the target by measuring the time for radar pulses to reflect back. So how much time it takes from radar to go to the and hit the surface and come back, right? So time recorded by system clock is in tenths of a second, but it is stored as an integer because 1970s storage was very expensive and integer storage was much faster and much cheaper. So for calculation, it was time was converted to a 24-bit floating point numbers because you need fractional numbers. So these integers were converted to 24-bit floating point numbers. So when you do this calculation, so depending on how many hours the missile system is in place, so you would find that the within 1 hour the drift uh, would be 7 meters from the range gate. It is out of range, but 7 meters is still within the range. I mean, your antenna is large enough to track that, but after 20 hours it's 137 meters, and that's completely out of the range. And no matter, I mean, what it does, the incoming missiles would not be detected, right? So target is outside the range gate after 20 hours of operation. And on the dreadful day, Alpha Battery, which was protecting the Dharan Air Base, had been in continuous operation for 100 years, over 100 years, and the drift was about 700 meters. So next day, uh, after the disaster, the problem was identified, and then the software was modified, this conversion, and more precise storage and calculations were incorporated to rectify the problem. So just to sum up today's discussion, what I had been telling, associative law need not hold. So these two operations, depending on the order in which these operations are performed, can yield different results, right? So computer arithmetic, these errors were analyzed, and entire thing developed into a scientific discipline by the efforts of two British mathematicians, Alan Turing and James Wilkinson, J.H. Wilkinson. We have Wilkinson Prize for numerical algorithms that is awarded every year. Alan Turing was known for artificial intelligence, for his work on artificial intelligence and cyber cryptography. So he was the person behind breaking the Enigma code of German cryptography. Okay, so IEEE arithmetic is a standard. Uh, when the computers were being developed, and floating point representations were causing complete chaos. I mean, different vendors would implement floating point arithmetic in their own way, whichever they found uh, advantageous or easier to implement. And the results were not comparable when the same program was compiled and run on different platforms. So, in view of that, and to bring down about a uniformity in the floating point representation, they adopted the IEEE came up with the floating point representation standard IEEE 752 in 1985, and since then all computer platforms follow that standard, and uh, those floating point numbers, the operations, floating point operations, they now behave reasonably uh, in a standard fashion. So we come back to this problem, counting to six, just as a uh, to cap up this lecture, today's lecture. So calculation of 1, 2 minus 1 is equal to 1. Calculation of 2, 1 over cos of 100 pi plus pi by 4, and then square of it. So it would be some value 2.00000 something. Third one, I find it really funny that Professor Nick Higham would make this error. You should realize that this is rubbish. You can't calculate arc cosine of 10,000. Cos inverse of 10,000 is not a defined mathematical operation. Cosine cannot have value greater than or 1, right? Minus 1 to plus 1 is the range of cosine function. So arc cosine of 10,000 doesn't make sense. So obviously, he obviously wanted to mean something else. I mean, 10,000 multiplied by arc cosine of some number and then redo that, invert that number and so on, such that this factor was aimed at computing 1 such that 3 multiplied by 1 would result in 2 point, I mean some approximation to 3. So 1 would be approximated by something close, right? So you can, that's a exercise for you to do, how to rearrange these terms such that you get something close to unity. And this is the example that I was referring to. Take 4, number 4, keep on taking repeated square roots, and then after you end up at 1, no matter how many times you try to square it, the result is always going to be 1. And then this number, you would again get something very, very unexpected. Man, not a number. And then this is a very, very large number which is outside the range of computer, and computer would immediately flag it as infinity. That is, it's beyond its computational or range of the numbers that it can represent. So that's all for today. Uh, the whole idea of today's lecture was to expose you to the limitations of computer as a machine. It's a very powerful tool, but not without its limitation. And it's important to understand the limitations of a tool before mastering that tool. So, any questions? Anyone?